There you go.
Okay. So hi, everyone. Welcome back. It's the second half of our rundown on linear algebra, given once again by Zachary Bradshaw. If you don't remember him, he's the dude who hosts the meetings. So take it away, Zach.
All right. So last time I showed you how to build up what's called a Hilbert space right from scratch, from a set. We took the set and just kind of kept putting structure on it over and over again until we got something that resembled a Hilbert space. And what I didn't tell you last time, which I should have told you about, was what a basis is. So let me first say what a basis is. So if you have a vector space V, of course, okay, there we go. If you have a vector space V, a basis for the vector space is the list of elements E1 through En, and each of these is inside of the vector space that has the property that there are, for any other vector, let's call it V, which is inside of the vector space, you can write V as a number A1 times E1 up to AN EN. Right, so this is what this means is that this set of vectors, this spans V. That's what this property means. Okay. And the other thing you need is that E1 through En are linearly independent. So if, let's just choose different numbers, C1, E1, up to Cn, En, if this is equal to 0, then we need that to imply that C1 equals all the other constants, and they're all equal to 0. If that's not the case, then there is some dependence in your vectors, and you're probably able to throw one away. Okay, so again, this property here is called linear independence. So together, if you can take any vector in your vector space and write it as a linear combination of the basis vectors, so I'm already calling them a basis vector, but as a linear combination of these vectors, and you have this property, the linear independence property down here, then your set of vectors is called a basis. So if it spans and it's linearly independent, then E1 through En is a basis for V. Okay, so there are many different bases for a vector space, and you can change from one basis to another by applying a unitary transformation, which I'll get into in a second. But one important result is that the dimension of V is, should I say this, the number of basis vectors. And it turns out that no matter what basis you use, they always have the same number of basis vectors. Okay. So there's a proof of that, which I won't give. So today the only things I'm gonna prove are extremely simple things because I don't have enough time to prove to you the spectral theorem and singular value decomposition, polar decompositions, and all that stuff. So the complicated stuff I will refer you to Nielsen and Schwang. Okay. So we have this thing called a Hilbert space. What does it have? Well, it comes with this comes with a field, right? And we can do scalar multiplication. Our field is always going to be C. So our Hilbert space is a vector space over C. So we can take a state, let's use bracket notation again, and we can multiply it by a complex number lambda, and this is still in a Hilbert space. We can also, we can add two vectors. This is still in our Hilbert space. These are just vector space properties. What makes it a Hilbert space is that inner product that we defined. So the inner product takes two vectors and it spits out a number. And that number we usually denote by this symbol. So on the left is the way a mathematician would write the inner product. On the right is the way a physicist would write an inner product. Okay. So last time I mentioned that you can think of this symbol psi as being a linear functional. And what that means is that this is the same thing as this function. So this is a function of the vector space. You can plug in a vector phi here where I put a dot, and it spits out a number, right? So these mean exactly the same thing. So there it is in physicist notation, there it is in mathematician notation. Okay. Okay, so there are loads of definitions to start out with. One of them is orthogonality. So if we let psi and phi be in our Hilbert space, then the inner product, so if the inner product of psi with phi is equal to 0, what this means is that psi and phi are orthogonal. Which is a really cool word. It's a generalization of the word perpendicular, I guess. Let's see, okay. So the way you see that, it's a generalization of that is you can draw the plane, right? And there's a vector that points up, which is 0, 1, and a vector that points to the right, which is 1, 0. And the inner product of these two vectors is 0 times 1, which is 0, plus 1 times 0, which is 0 times 0. So these things are orthogonal, aka perpendicular. So the perpendicular is the more geometric word, I guess. But anyway, so whenever you have an inner product, you can always define something called the norm. So this is the norm induced by an inner product. It takes a vector, let's call it psi, and the way we define it is to be the square root of the inner product of psi with itself. So the norm squared would just be the inner product of psi with itself. Okay, so that brings us to a definition. So here's a definition. A unit vector is a vector psi with norm of psi equal to 1. So it's exactly what it sounds like. And we say that psi is normalized. So in this case, we say psi is normalized. And that's for a reason that we'll see when we get to the actual quantum mechanics section. Okay, so then we can go a little further here. So psi and phi are orthonormal. if they are orthogonal and unit vectors. So psi and phi are both normalized and they're orthogonal to each other, then we have, then they're called orthonormal. And so one thing we can construct is whenever we're given a basis, we can always construct an orthonormal basis, meaning every vector in the basis is orthonormal to every other vector. And the way we do that is by the Gram-Schmidt procedure, which I'll just write to you. I kind of want to prove it to you, but I know there's a lot to say. So here's the Gram-Schmidt procedure. So if I give you a basis, let's say it's omega-1 through omega d, where d is the dimension of my Hilbert space. This is not necessarily orthonormal. How can we construct another basis which is orthonormal? Well, we define the first element of the basis. We call it V1, and we define this to be omega-1 over the norm of omega-1. So the effect of dividing by the norm is you take omega-1 and you turn it into a unit vector. So if you take the norm of this, this is 1 over the norm of omega-1 times the norm of omega-1, which is just 1. So it does indeed have norm 1. Okay, but let me erase that for a moment. Okay, I need to move this. Okay, so then what do you do? Well, for all the rest of them, so for 1 less than or equal to, let me say, k less than or equal to d minus 1, what we do, we define vk plus 1 to be wk plus 1 minus the sum from I equals 1 to k of vi inner product with omega k plus 1. I'm going to keep moving this thing once I put it over here.
I know you can be very small, right?
Yeah, but I like to see people. All right. And then we divide by the norm of this, which I'm going to refrain from writing again. So this is the norm of exactly the same thing. So dividing by the norm obviously makes this thing a unit vector. That much is clear. So what you have to check is that V1 through VD are actually orthogonal to each other. So it's not difficult to check. You have to just maybe I should do it. I don't know. Do you think I should do it?
Make a poll.
All right. Should I check this, guys? I don't know.
I'm gonna bring no.
All right. Let's say no. Okay. Let's just move on. So I encourage you to check to make sure those are all orthogonal. It shouldn't be too tricky, but if you get stuck, just let me know. Oh, that's perfect spot for it, actually. Okay. So in quantum computing, we will see a lot of what's called the outer product representation. So I'm just going to tell you what an outer product is. So an outer product is just a ket followed by a bra. Whoops. And I'm here to tell you that this is an operator. And so your question should be, well, what does the operator do? And the answer is, well, if I plug in, I don't know, omega, let's say, what does it do? So, well, here's my operator, and I want to apply it to omega. And the way we do that is exactly what it looks like. we just take the inner product of phi with omega. Now this is a number. That's a number. This is a vector. So we can move the number to the other side just to make it a little cleaner. So the effect of this operator is to take omega and transform it into psi times this factor here, which is the inner product of phi with omega. That's the outer product. So this kind of shows the power of the Dirac notation. You know, things just kind of fit together. When I talk about this operator acting on this ket, well, I just kind of slide them together, and it kind of, the notation just works by itself. Okay. So if you have a basis, let's denote it by I. One, two, I don't know, D. So the other way to write this is 1, 2, all the way up to D, right? So if I give you a basis, you can take the outer product of each individual ket with itself, right? And you can sum them up. And the other way to write this in sigma notation is the sum from I equals 1 to D of I outer product with itself. And I claim that this is in fact equal to the identity operator. So when you apply it to a vector, it does nothing. Okay. So let me prove that to you. Here's the proof. Okay, so let's let V be a vector in my Hilbert space. So I want to prove the thing that's right above. I want to prove this. So the sum from I equals 1 to D of I outer product with I applied to V, right? Well, this is equal to the sum from I equals 1 to D of I inner product of I with V. Okay. I can move that. Oops, sorry. I can move that. So remember, an inner product gives you a number, and this guy is still a vector. So this is I inner product with V times I. Now, you can always write your vector V in the following way. Sum from I equals 1 to D. And what you do is you project your basis elements onto V. So, well, maybe I'll say it like this. You can always write this like this. There are constants Vi such that V can be written like this. This is the span property of the basis, right? So this is because the basis spans the Hilbert space. And you can ask the question, what is Vi? Let me scroll a little bit. So what is Vi? Well, you can take the inner product with, sorry, let me ask, what is Vj? You can take the inner product with J. So this is J. There's a Vi here, and there's an I there. Right. And the Vi, this is a number. We can pull it out. There's still some there, though. And this guy, Well, we know that our basis is, I'm assuming, by the way, our basis is orthonormal. If it's not, you can find one that is, right? And you can start from scratch with that one. So that means that if j is different from I, then this is equal to 0 for j not equal to I, and it's equal to 1 for j equal to I. So what does that mean? That means the only term that survives here is Vj. Right? Everything else has a 0 multiplying it. So that tells me that Vj is equal to the inner product of j with V. So that tells me that this guy, so let's go back up, this is equal to the sum from I equals 1 to d of Vi I, which is exactly my vector V. So at the end of the day, what did we do? Whoops, I don't know what I just did. Okay. So we applied the operator to an arbitrary vector V, and we tracked what it did. And we made it all the way down to the end here. We said, okay, what does it do? It just gives me V again. So then this guy must be the identity operator. What it does is absolutely nothing. So that proves the statement. So there you go. There's a square for the end of the proof. All right, I'm going way too slow. All right. I wanted to prove to you the Cauchy-Schwarz inequality, but I don't think I have time. So here it is. So Cauchy-Schwarz. Cauchy-Schwarz inequality says if U, not U, V, W are in my Hilbert space, then the following inequality holds. We have the absolute value of the inner product of V with W squared is less than or equal to the inner product of V with itself times the inner product of W with itself. So you can also write this as, remember, this is the norm of V squared, and this is the norm of W squared. Okay. So there's another inequality that generalizes this. I'm not going to write it here, but if you want to look it up later, you can. It's called Holder's inequality. Okay. But just so you have it, there you go. Okay, so Cauchy-Schwarz comes up all the time. It comes up in the proof of Heisenberg's uncertainty principle, for example. But I'm going to leave that to whoever's talking either next week or the week after. Okay, so now the very, 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 very important topic of the day is Eigeneverything. All right, eigenvalues, eigenvectors, eigenspaces, eigenstates, Eigeneverything. So an eigenvector or eigenstate, if you like, they mean the same thing. So let's call it V with eigenvalue lambda, this is a number, is a pair, so the vector and then the number, such that whatever operator we're considering, A, when we apply it to our vector, gives us the number lambda times that vector. So I should say that this is an eigenvector for A with eigenvalue lambda. Okay. So whenever you talk about an eigenvector, it's associated to an operator. So if V is an eigenvector for A, it's not necessarily an eigenvector for the operator B, for example. So different eigenvectors can have the same eigenvalue, not necessarily. They could be different. But in general, you don't know one way or the other. It could be either one. But an eigenspace associated to the eigenvalue lambda is the collection of eigenvectors with eigenvalue lambda. So we usually call it E lambda or something along those lines. Okay, so it's essentially, if you have two eigenvectors for the same eigenvalue lambda, then the eigenspace would be the linear span, so the space of all linear combinations of those two eigenvectors. So just as an example, I guess. So if A has eigenvalue lambda equals 1, and that one eigenvalue has two eigenvectors, so let's say V and W are the eigenvectors, then the eigenspace E1 is equal to the set of all vectors AV plus BW, such that A and B are complex numbers. Okay. So this eigenspace is a subspace of the Hilbert space. So what does that mean? It means if you take two vectors in here and you add them together, then it's still a vector in the eigenspace. And if you take a complex number and you multiply it by a vector in here, well, it's still in the eigenspace. Okay. So that's not hard to prove. It's line by line, just unpack the definitions. So that implies it's a subspace. Yeah, so I wanted to point this out. It's not in the book. So if E lambda is an eigenspace for an operator A, then E lambda is invariant under A. What that means is that if you multiply A times a vector in your eigenspace, so I'm assuming psi is in E lambda here, well then this is equal to lambda psi, which is still in my eigenspace. Okay. So A, when you restrict it to the eigenspace, is just the same thing as lambda times the identity operator. Okay. 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 I don't think I have time for that. Well, I got lots of pages here, so I think you're really overestimating the amount of time I have. Okay, so adjoints and Hermitian operators. Okay, so here's the mathematician way to define an adjoint of an operator. So the adjoint of A is the unique, that's important, unique operator, which we call a dagger, such that when you take the inner product of V with A on W, so just take two random vectors from my Hilbert space, doesn't matter what they are, just call them V and W. When you take the inner product and you multiply A times W, this is the same as a dagger on V inner product with W. So I wrote it in the mathematician notation because this is not very clear when you write it in the physicist notation. Because everything's sort of just sandwiched. So this always just looks like this in the physicist notation. And so it doesn't really tell you what's going on here. Okay, so the adjoint of A is the unique operator such that this is true. And we call it a dagger. Okay. That elongated plus is meant to be a dagger. Okay. Okay, so once we define that, we can define what a self-adjoint operator is, what a unitary operator is, blah, blah, normal operators, all these great things. So this dagger, by the way, is not always called the adjoint. In physics texts, you sometimes see it referred to as the Hermitian conjugate. So adjoint equals Hermitian conjugate. Okay, so all right, so let me say this. So when is some operators that we care about are Hermitian operators. So a Hermitian or self-adjoint operator is an operator A such that a dagger is equal to A. Okay. We say that it's unitary, so I'm not going to write all this again, but unitary means a dagger A equals I, and it works the other way as well. A times a dagger is also I. Okay. And last but not least, normal. So a normal operator means a dagger A equals a dagger. So we notice a couple things. A unitary operator is already normal, right? So unitary implies normal. It's just a little stronger because it tells you what the product is. It's just the identity. And Hermitian operators are also normal, right? Because if you're Hermitian, so if you're Hermitian, then a dagger is just A times A. Hermitian means a dagger is equal to A, which is a dagger times A, right? So Hermitian implies normal and unitary implies normal. And that'll be important in a second. Okay. I want to mention, I really wanted to prove this one too, but here's a lemma. The Hermitian conjugate of A times B is the same as Hermitian conjugate of B times the Hermitian conjugate of A. So AB dagger is B dagger, A dagger. Okay. So the proof of this is just definition unpacking again, right? You have to show that so the adjoint of, oh, sorry, no, that's not what I want. I want A times B on W. The adjoint is the unique vector or unique operator AB dagger, such that this inner product, these inner products are equal. And what you can do is you can just move the A over here and then move the B over there. And what you get is B dagger, A dagger, V with W is equal to this guy, which means that these two are equal. So since the adjoint is unique, these two must be equal. That's the entire proof. So I encourage you to go through that in detail. That's the gist. Okay. I forgot to mention one more type of operator. So a projector is a Hermitian operator such that it's equal to some from I equals 1. Well, I don't need to say Hermitian if I write it like this, but it looks like this. That's a projector. The other way you can define it is a Hermitian operator such that P squared equals P. Okay, so normal, unitary, blah, blah, did that. All right, here we go. So here's why I was pointing out that unitary and Hermitian operators are normal. We have what's called the spectral theorem. All right, so I'm just gonna kind of write it. So if M is normal and it acts on some vector space, let's call it V, okay, then there is a basis for V. There's always a basis for V, but it's a special basis set for which M is a diagonal matrix. So we just call that diagonal. So I've been talking about operators this entire time. Every operator in finite dimensions, every operator acting on a finite dimensional vector space has a matrix representation. Well, that's slightly wrong. Every linear operator acting on a finite dimensional vector space has a matrix representation. Okay. So whenever I talk about the operator, I don't know, the NOT gate, right? It has a matrix representation. And the NOT gate, for example, is 0, 1, 1, 0, right? So I guess we'll see what that means as we get further along and actually start doing some physics. But anyway, so this is true for any normal operator. And we know that Hermitian operators and unitary operators are already normal. And projectors are Hermitian operators, so those are also normal. So all these operators, which are really the only ones we really care about in quantum mechanics, they all have a basis for which the operator is a diagonal matrix. So diagonal just means that it looks like this. There's 0 everywhere else. Okay. So this is one of the proofs that I wasn't going to do because it's too long and it's a Nielsen-Twong anyway. Okay, so the spectral theorem is pretty important. It allows us to deal with functions of operators, but I don't think I really get into that here. But I'll explain it if we come across them at some point, which I'm sure we will. So tensor products. So if I have, tensor products. If I have two Hilbert spaces, H1 and H2, then I want to be able to define the tensor product of these two Hilbert spaces, which is sort of just a product of vector spaces that preserves the inner product structure. And the dimension, we want the dimension of H1 tensor H2 to be equal to the dimension of H1 times the dimension of H2. Okay. Okay, so how is this thing defined? Well, what we do is we take H1 tensor H2 and we define this to be the space of all linear combinations of vectors of the form I tensor J. So I'm not writing this in a good way. Let me move this to the side. Sum over I and J, and I need a constant here. C I J I tensor J. I'll explain this. Okay, so what I mean by this is if this is a basis for H1 and J, this guy is a basis for H2, then a basis for H1 tensor H2 is the space of tensor products, or the set of tensor products, where we sum over, or not sum, but index over I and J. So what you have to do is you have to treat this as like a brand new object, right? So let me just give an example with the bracket notation. So if I take my Hilbert space H1 to be C2, and I take another Hilbert space, also C2, well, a basis for this one is the 0 and 1 cats, and a basis for this one is also the 0 and 1 cats. So if you don't remember from like that, I think the first talk, this is the 1, 0 column, this is the 0, 1 column. Okay, but we're not going to use that notation here. Anyway, so the basis for H1 tensor H2, so H1 tensor H2, this is going to be C4, and the basis is going to be 0, 0. Let me write it with the tensor first. 0 tensor 0, 0 tensor 1, 1 tensor 0, and 1 tensor 1. So my basis for the tensor product is this, and we treat these things as sort of new quantities. These are the basis vectors. Anyway, so I'm telling you that this is a Hilbert space, so I have to tell you what the inner product is on it. So if I take 0, let's say 0 tensor 0, and I inner product that with, I don't know, let's say 0 tensor 1, for example, I have to tell you what that is. What we do is we define this to be the first element inner product with the second, or the first element of the second guy. So this is 0 tensor, or inner product of 0 times, because this is a number, this guy inner product with that guy. So this is 0 inner product with 1. Okay, so we do the same thing for any vectors in the tensor product space. All right, and now let me make our life simpler by reducing the notation. So 0 tensor 0 means the same thing as 0, 0, and that means the same thing as 0, 0, like that. Okay. So we define these all to be the same thing. Okay, so this is probably the more familiar notation that you're used to if you've seen quantum mechanics. Okay, so let's see, what can I say that's important? Okay, so I have to give you the tensor product of operators. So if I have two operators A and B, what is the tensor product of A with B? Well, what it does is it maps from H1 tensor H2 to itself. And the way it does it is it takes an element, let's call it, I don't know, ij, right? And what it sends it to is A tensor B acting on ij, and I define that to be A acting on I tensored with B acting on J. Okay. So A is an operator that maps from H1 to H1. B is an operator that maps from H2 to H2. So A tensor B is an operator that maps from H1 tensor H2 to H1 tensor H2. And the way it does it is it takes an element of the tensor product, right? And it just kind of splits it up into its pieces. So I tensor J, and it applies the one that acts on H1 to the element from H1, and it applies the one that acts on H2 to the element from H2. Okay. So it's really the only way you can define this. And one question that I think Marguerite and I are about to almost tackle, sort of, is if C is an operator on H1 tensor H2, when can we write it as the tensor product of two other operators, one of which acts on H1, the other on H2? And well, I mean, there's a lot of different reasons that might be true. And so we're exploring one such reason that might be true.
Yeah.
Okay, so I don't have enough time to do functions of operators. Yeah. I think the last thing I'll say is there are two useful decompositions. There are actually three. I didn't write one down apparently. But there's the polar decomposition. And again, the proofs of these are in Nielsen and Schwang. But polar decomposition. So if A is a linear operator acting on a vector space V, then we can always write it as A equals uj, or A equals ku for some unitary u and positive operators jk. So the operators j and k here are actually unique. You won't find any other ones other than the ones. But and j, so we actually know what these guys are. J is equal to the square root of a dagger a, and k is equal to the square root of a dagger. And actually, it goes further. If a is invertible, then actually the unitary is also unique. Okay. So that's the polar decomposition. I said that j and k are positive operators. What that means is that if you take the inner product like this, so apply j to psi and then take the inner product with psi, this is always greater than or equal to 0. Might just be greater than 0. I don't remember.
That's positive semi-definite.
Yeah. So we want greater than 0. Yeah. Okay. So then the other decomposition is the singular value, which uses the polar decomposition in its proof. Singular value decomposition. So this one says that if A is a square matrix, so A square matrix, right, then there are unitary matrices, then there are UV unitary, and D diagonal. All right, with non-negative entries. Yeah. Okay, with non-negative entries, such that A is equal to, let's see, UdV, right? Yeah, UdV. So the diagonal elements of this matrix D, by the way, are called the singular values of A. Okay. So I don't really have enough time, I guess, to do the Schmidt decomposition, unfortunately, but very useful in quantum computing. So definitely read about the Schmidt decomposition. It's in Nielsen and Schwang, and I think also KLM. Yeah, it'll definitely come up again at some point. But all right, so I hope that run through of a semester's worth of linear algebra was you at least learned something.
Or if not, yeah.
All right, anybody have any questions?
Apparently we helped Roy with homework. So.
Lots to think of. Yeah, I agree. Let's see. Is there anything I can point out that's like worth a discussion?
I think you could very, very quickly just mention how you do a function.
Oh, function of an operator. Yeah.
Spectral decompose it and then do it to the eigenvalues.
Yeah. So what Marguerite's talking about is something I skipped over because I didn't really have enough time. So if you see something like this, so if you have a function f and they plug in an operator, that might look funny, but you can define this. So if A has a spectral decomposition, then it can be written as A equals the sum over I of lambda I, I, right? Right here.
Yes, because that's
Yeah,
there should be projectors.
yeah. And the lambda I are the eigenvalues of A. Okay. Then f of A, well, the way we define this is to be the sum over I of f of lambda I. Okay, so let me give you a concrete example. So if you take, for example, the matrix theta, 0, 0, minus theta, let's say. And I ask you, what is the exponential of this? So exponential of this matrix. Well, the exponential is only really defined on the reals, but we can define an exponential this way, right? And what that looks like is, well, this is already written in that form. This is the exponential of, let's see, that's theta times 0, 0 plus minus theta. I'm going to write the plus minus theta of 1, 1, like that. Move over. And if you want it in the sigma notation, that's the exponential of yeah, I'd have to actually index that constant, but all right, so I don't want to do that. But how do we do this? Well, we apply the exponential to the constants. Okay. What does that look like in matrix form? Well, the 0, 0 term is the top left of the matrix. So that's the exponential of theta, which is e to the theta. And then the 0, 1 term is this one over here. There's nothing there, so that's 0. The 1, 0 term is there. There's no 1, 0 term, so that's 0. And the 1, 1 term is the bottom right, and that's e to the minus theta. So if somebody asks you what's the exponential of this matrix, well, it's just that matrix, okay? So in general, if you have a diagonal matrix, all you have to do is apply the function to each element on the diagonal. But it's not true that if you have A, B, C, D, and you want to apply F to this, this is not in general the same thing as F of A, F of B, F of C, F of D. And you can see that already here. Because if you applied the exponential to everything here, well, you would have e to the 0 in the bottom left, which is 1, and e to the 0 to the top right, which is also 1. But we have zeros there instead. So don't fall for this, I guess.
Just especially because every time I saw a square root of a matrix the first time, I was like, what does that even mean?
Yeah.
And I think that this makes you less angry than when physicists like exponentiate a matrix and they're just like, well, just take the Taylor series.
Yeah.
Which definitely always exists.
All right. Any other questions, concerns? It was a lot. I'm sorry.
I have a question.
Yes.
When we're dealing with like sums or like any type of Hilbert space, excuse my terms that I use because I'm not a math major, so I'm gonna say stuff that probably is not exactly correct. But I'm curious about like whether in quantum computing it's applicable to use like finite spaces or if it's usually infinite like spaces. The reason I'm asking this is because in my class, they took a pause like when we were looking at sums and said, okay, this is like if we have a finite space, but in quantum computing, usually you would use an infinite space, or that's like an application to it. So I didn't really know what that meant. So I wanted to hear.
It's actually the other way.
Really?
So, yeah. In quantum computing, your Hilbert space is almost always finite dimensional. Like, the reason is, I mean, how do you construct a quantum computer with infinitely many qubits? You know,
Right.
so you're always going to deal with a finite dimensional Hilbert space in quantum computing. However, in quantum mechanics, you very regularly deal with infinite dimensional Hilbert spaces. One example is, I don't know if they maybe showed you this space. It's L2 of R. It looks like that. But it's just the space of square integrable functions. So all the functions for which this integral is finite. But this is an infinite dimensional Hilbert space. So you'll deal with things like that in quantum mechanics, but it's usually kind of behind the scenes. They don't really tell you that if you're a physicist.
There's one thing I can think of for quantum computing is if you're doing like continuous wave. So for all the practical quantum computing, you're doing like photons right now. But you could have like, I don't know, a laser, and your qubits are your LG modes or something, and that's infinite dimensional. But almost nobody actually does quantum computing that way, because that's I mean, they're good for particular applications, but when you're trying to design a universal quantum computer, although they're technically equivalent, it's just much easier to do the discrete version, where you have, like Zach said, like finite dimensional spaces that you're working with.
So the picture to have in your head is like a circuit. You know, maybe it has 3 qubits, right? Maybe this one's 0, maybe that one's 1, maybe this one's like the plus state, whatever. And you have these operators that are being applied to maybe this one to 2 qubits, maybe this one to 3 qubits. And what's happening is this guy, so as these pass through this gate here, we're applying U to the joint state 0, 1. And where does 0, 1 live? Well, 0, 1 lives in C4. Right. So it's a 4-dimensional Hilbert space.
It is true that it is an infinite space. There are infinitely many vectors in it.
Mm-hmm. It's just not infinite dimensional.
Right.
What about when you're scaling it though? Even though obviously, like, would you want to consider infinite dimension? I'm talking about scaling quantum computer, by the way. Like when you're thinking about scaling qubits, would you even consider the case of an infinitely dimensional Hilbert space, or would you still in that case want to only look at like very large space, but like not infinite?
I mean, your space, you can let your space go to infinity, but at the end of the day, when you're doing quantum computing, the only gates you care about are very small dimensional ones. So I think the C0 gate and Hadamard are universal.
C0, Hadamard, SMT.
Yeah, the T gate. Yeah, I mean there's a 2 qubit gate and then a couple 1 qubit gates you need, and then you can construct any other gate. Doesn't matter how big they are. So on the operator side, you only ever care about small Hilbert spaces. But I mean, technically, you know, you can increase the number of qubits here, and the actual Hilbert space will increase its dimension.
2 to the n.
Yeah, 2 to the n. Yeah. As you add a qubit, the dimension of the Hilbert space goes up by another factor of 2.
Again, really stress, it is an infinite space. It's not infinite dimensional.
Gotcha. Okay, cool. Thanks, guys.
Mm-hmm. All right. Any other questions? Okay.
Always be careful of physicists saying math words also, right?
Yeah. Condensed matter theory is, I think, mostly quantum field theory. So that is a infinite dimensional scenario. So he's justified in having you want to know it.
Yeah, he just presented it in such an annoying way because he was like, oh, we're not going to look at this, but it's very useful in quantum computing. And I was like, oh, okay. And I asked him why after, and he like didn't really explain why that well. So that's I wasn't satisfied with what he was giving me.
I should say also, by the way, that half the things I said today are not actually true for infinite dimensional Hilbert spaces.
Yeah.
Yeah, that's what he was saying. So that's what I was also wondering. Like, yeah, okay. But it doesn't change much, right?
You run into like technical issues. Like so when you define the adjoint of an operator in infinite dimensions, you have to deal with the domain of the operator. So for a finite dimensional Hilbert space, the domain of the adjoint is the same as the domain of the original operator. So you have no trouble there. But in infinite dimensions, that's not true. The domain of the adjoint is actually larger than the domain of the original operator in general. And so you have to prove that actually they're exactly the same in order to show that something's self-adjoint.
Jeez Louise.
Yeah,
Thank you.
it's a pain, let me tell you. If you're
Oh,
curious,
God.
that's all in Hall's book. It's quantum theory for mathematicians or something like that. Yeah, it's very good.
Yeah, this is why I don't go into math. I don't know so much about the math that I use in these classes. It's kind of bad.
Let me stop the recording so it's not too long.
I think I